Welcome back to Calculus with Applications for our third week of remote learning. Before proceeding with this video, you should open the Integrating Functions Below the X-Axis video capture sheet provided. You will be asked to complete tasks in the document throughout the video. We're still in Unit 5, where we're studying the integral. In preceding lessons, you have learned that the definite integral can be described in terms of area. You have learned to make approximations of various kinds to estimate the area under a curve, making successively better approximations until, in the limit, we obtain the exact value of the area under the curve. In this lesson, we'll learn how to evaluate definite integrals for functions that may drop below the x-axis, like the function pictured on this introductory slide. Recall from previous lessons that the area between a non-negative function and the x-axis on the interval a to b can be written as the limit of a sum of rectangles as the number of rectangles approaches infinity. And this can be written in our newer compact integral notation. Notice that this result holds for a non-negative function, that is, a function that never lies below the x-axis, like the one pictured. In the first two lessons, we have been careful to present you with examples of functions that were above the x-axis. At the end of the preceding lesson, we asked, what do you think happens when a function lies below the x-axis? What meaning could the definite integral have for a function like g, pictured here? You also had an opportunity to explore an example of such a function using the applet. You notice that when a function lies below the x-axis, we obtained a negative value for the definite integral. Why does this occur? Let's take a closer look at the limit definition in order to see why we're getting a negative value for the integral. The function values in blue are negative. Furthermore, since we integrate from left to right, the change in x, delta x, is positive. When we multiply a negative number, the function value, and a positive number, delta x, we obtain a negative number. The definition then calls for us to sum all these small negative quantities. Clearly, the sum of negative quantities is negative. Armed with this new understanding of integrals, let's turn our attention to a function that has intervals for which the function is positive and negative, like the one shown. Suppose we want to evaluate the integral of the function f of x from 0 to 5, shown here. Notice that some portions of f lie above the x-axis and some portions lie below. If you knew the area of each of these regions, could you determine the integral value? Pause the video and see if you can make this calculation. How did you deal with the portion of the function below the x-axis? If you understood that the integral from 2 to 4 would be negative 2, you are correct. Putting this all together, we find that the integral on the entire interval from 0 to 5 is 1.5. The total area of the three regions is 5.5, but the integral value is 1.5. In some sense, the integral gives the net area instead of the area. Let's do one more example to help us understand the difference between area and the definite integral. Consider the function f of x equals negative 12x squared times x minus 2. Let's find two things. First, what is the integral of f from negative 1 to 3? And second, what is the area between f and the x-axis on this interval? Pause the video to consider the difference between these two questions and how you might approach each. Both have something to do with the area of various regions on the graph, where the zeros of the function play an important role in splitting up our integral into separate regions. I've used technology to compute the integral over each of these separate intervals. Pause the video again to see if you can answer our two questions using the numbers on the screen. Remember that the integral for the red region below the x-axis carries a negative sign. For the integral, we just sum 11, 16, and negative 43 to obtain negative 16. We can infer that the amount of area below the x-axis in red exceeds the total amount of area above the x-axis in blue and green. It's also worth mentioning that we can compute this entire integral all at once using technology, and typing in a single integral from -1 to 3. For the area between f and the x-axis on this interval, we just treat each area as positive and then compute the sum to obtain 70. Note the use of the absolute value on the third integral, and notice once again the importance of splitting up our integral around each of the zeros of the function. At this point, it may seem like the disagreement in these last two answers is an undesirable property of the integral. But as we move forward in our study of integration, you will see that both computations are extremely useful. The example we next turn to is particle motion.